And I'll go over here and let me also get my screen sharing started here. All right, welcome everyone to IPC's PCB Design Fundamentals Part 2. My name is Chris Moyer and I will be your instructor for this course. We're going to spend a minute here. Kelly Allen, who is my partner in this, will be joining us here shortly. We'll go around the room though and have a few introductions, but a little bit of background about myself first here. I'm not going to go into a heavy background as I do have it available on our Edge page. And the first thing I want to touch base on is our IPC Edge. I hope by now everybody has been able to get into the IPC Edge area here on the web page. This is going to be our main area of interaction, coursework, recordings, access to the course material, all that kind of good stuff. When you first get in here, there is a UTC date and time widget here up in the upper left corner here. This one is static. It only refreshes when we update the web page, when you do a refresh of the web page. I will point out later a different one that we have available that is continuously updating, and we'll look at that more towards the end. When you come down in here, there is an area for your courses here. And I do want to point out one other thing, and I'm going to put this in the chat window right here. There are two ways to get to the IPC Edge page. If you go into the main ipc.org, where the IPC organization's main web page is, and go to the education area, you can get into IPC Edge there, but at this time, that area only shows your current courses. However, the direct path in is what I've just put here in the chat window, my.ipcedge.org right here. If you go to that page, you'll get this version of the interface, and this will also allow you, after you've completed courses, to go back in and continue to review courses you've already completed, go back into them, review recordings again, and so on. Okay, so I'm going to go over here, and I'm going to go into our course right here. So in our course right here, we'll have the Edge page right here. And I will point out that there is a little bit of, I'll do a short walkthrough. I have a slightly longer walkthrough recording video, which I'm going to get to here in just a moment. But there's a opening part up here with update personal info. This is a boilerplate that comes with this LMS tool that we're using. You do not need to update that, as we have all of that information already as part of your registration. We then have a read before you begin, grades and course completion, the syllabus for the course here, the Zoom registration link right here, and then we have some browser settings, and then I have a resources area right here. Throughout the course, we'll go through a number of these different resources. These are just different resources I've put together that we will find helpful. Below these, we also have these how-to videos. So I have a slightly longer version of an introduction about myself, a little bit about my background, my history, and so on. Video you can walk through here. A slightly longer walkthrough of this IPC Edge interface here, as well as a video here on download, install, and setup of our Altium tool, which you will have a 1-year license of as part of this course, as well as a few other helpful links right here. Okay. So with that, before we get going on the course itself, what I do like to do is start by going around the room and introduce ourselves. Just name, where you're from, and what brought you to the course. So, just tell us, you know, uh, tell us your name, tell us, where you are, because we've got students from all over the world in here. So, are you here in the States? Are you overseas in Europe, down in South America, Asia, wherever you're at, let us know where you're at, and let us know, um, what you do and what brought you to the course. Just a quick minute or two each. So we'll start right here. I'm going to go up to the top of my list, and we'll start with Alonzo. Alonzo, go ahead and introduce yourself.
Hey, morning. I'm from Mexico. I work for a company where we don't used to do the PCBs or electronics, and now we are trying to take control of that. So that's why I'm here. Good morning, everyone.
Excellent. Welcome, Alonzo. Okay. And then Brian is next. Brian, would you like to open your mic and say hi?
Yep. Yeah, I'm Brian Robinson. I'm in Worcester, Ohio. Um, I just recently started with the PCB layouts and that, but I've been doing engineering work for close to 10 years now.
Cool. Excellent. All right. And then we've got Edson is next.
Oh, hello everyone. My name is Edson Camilo. I'm working here in Brazil for automotive industry, Magneti Marelli, and I am working with PCB many years, and I use the Cadence, Mentor Graphics, and Altium CAD tools too. So I'm in this course to improve my classes related to PCB. There are much to understand related to PCB. That's the reason I'm taking the course. So
Excellent.
welcome. So thank you, Chris, to
Yeah.
share your experience with us.
Yep, no problem. Okay, and looks like Faisal. Am I pronouncing that right?
Yes, hello.
Excellent.
My name is Faisal Hilevi. I'm from Saudi Arabia, and I'm working as an electronics engineer where I develop hardware and PCB boards. So I needed this course to enhance my knowledge into this field.
All right. Excellent. Welcome, Faisal. All right, and then it looks like we got Dennis Dahlquist next. Dennis, introduce yourself. Let us know where you're working and what brought you to this course.
Hello, I'm Dennis Dahlquist. I'm consulting engineer, and I've been interested in the particular topic, and looking forward to working with Chris and IPC. Thank you.
And by the way, Dennis, we don't need to use our videos here. It's just going to suck up the bandwidth, so feel free to turn your camera off. Thank you. All right, and then we have James next.
Hey, I'm Jake Prather. I'm an electrical engineer for Pradco Outdoor Brands. I'm responsible for validating PCB designs. So I've been filling this position for about 6 months and looking forward to learning from you, Chris.
Excellent. Welcome, welcome. And Jesse's next on my list.
Hi, I'm Jesse Kemper. I'm out of Dayton, Ohio, and I took this course to try to gain further experience in PCB design.
Excellent. Welcome, welcome. And John is next.
Hello, I'm John Waller. I'm from the UK. It's 4 o'clock in the afternoon. I'm usually on my way home. Been an electronics technician for 22 years in the oil and gas industry, and I wanted a break. So giving this course a go to move into design.
Excellent. Welcome. And then Mattia is next.
Hi, Mattia here from Austria. I've been working for NXP for some 10 years almost, and doing a lot of validation. And we just want to bring up our team according to the IPC standards. Thanks.
Excellent. Welcome, welcome. And then Navia, am I pronouncing that correct?
Yeah, that's right. Hello, everyone. So I'm basically from India, but I work in Germany, Munich, and I've been working in the hardware development industry since 3 years now. And I use Altium every day, but still I want to learn more. So that's why I'm here in the course. I'm looking forward to learning more from you, Chris. Thank you.
Excellent. Welcome to the course. And then Niti, am I pronouncing that correct?
Yes. Hi everyone. My name is Niti Preet. I work here in Canada as electronics technologist. I just started my career like 2-3 years ago. Recently, I've started getting projects that require PCB designing. I started learning a little bit from YouTube videos, but wanted an in-depth learning for circuit designing. So here I am.
Excellent.
Thank you.
Welcome, welcome. And then Roshan, am I pronouncing that correct?
Yeah, hi, I'm Roshan. I'm an electronics engineer based out of Cambridge, UK. However, currently on shoddy hotel Wi-Fi on business in Germany, so I do apologize for the connection. I do little bits of software and PCB design, looking to start my career doing things with from best practice as opposed to learning lots of bad habits early on.
Mm-hmm. Excellent. Welcome, welcome. And then finally, it looks like we got Sulan out there. Sulan, are you able to open your mic and introduce yourself?
Oh, good day. My name is Sulan. I'm in the education industry, doing certification for IPC as well. So I'm looking forward to learning from Chris and also to work with IPC on some of the projects. Right. Thank you.
Excellent. Welcome, everyone. All right. So there's two other folks from IPC who usually are able to join us here this morning. Kelly is one. She will be joining us here in a few minutes. I'll let her introduce herself when she gets here. But the other person is Ivan Santa Cruz. I'm going to put both of their email addresses in the chat window for everyone. So Kelly is going to be our basically my partner in this. So if there's any issues you have, can't access the course, any kind of issues like that, scheduling, any kind of problems like that, let Kelly know, let myself know, and then Ivan Santa Cruz, he is going to be our technical point of contact. If there's any issues like you can't get into the DRM standards, you can't get into uh, you're having trouble accessing the course, you can't find the recordings, anything of that nature, please let Ivan know. Again, actually feel free to always copy all three of us on any of your questions, because one of us will be able to take care of you on whatever your issues are. All right. So with that, we'll go over here and we'll get started here and go through our introductions here, or get started here with our first round of slides. Okay. And actually, before we get started with the slides, there is one other comment I want to make, and that's a little bit about the structure of my course. So this course meets 2 days a week, Mondays and Wednesdays. I'm in the Pacific Coast here in the States. I'm in California. So I'm in Pacific time. So it's my 8 a.m. to 10 a.m. in the morning. I believe we've got it as like 11 a.m. to 1 p.m. Eastern time in the States, and various other times around the globe. So we do meet 2 days a week. The structure of my course is what I call the see-do structure. So typically the first day of instruction of the week, I'll be presenting new slides, new material. And then the second day of instruction of the week, we'll be applying that material to hands-on practice in a project. The project is there solely for practice. We do highly encourage everyone to do as much as they can in the projects, but do not be concerned if you're not able to complete the projects, as they will not have affect your pass-fail of the course. That will be a final exam that we take at the end of the course. Okay, that being said, the course does meet for 2 hours. I do try to schedule a break right about the hour mark, right about the midpoint mark, but please feel free if you need a break to raise your hand or open your mic and ask, anything of that nature. And that's the other thing about my courses. I am a very interactive instructor. This is not intended to be a webinar style instruction where I lecture for 2 hours straight and you hold all questions, still a question and answer period at the end. This is intended to be more like you would a university or secondary school type of course, where it's very interactive. By all means, ask questions if there's anything you need me to go over, or have a question, even if it's tangential, even if it's not directly related. Please ask your questions. I will also, throughout the course while I'm lecturing, I will often stop and ask, is there any questions? Does everybody understand what I'm talking about in point A, B, or C, or whatever the case is? So I do try to make my course very interactive. That is how I teach my courses. That's how I find them to be the most effective. So please, by all means, put a question in the chat window, use the little raise the hand icon in the participants view of Zoom, or just open your mic and ask a question. I very much appreciate those and look forward to those. This is, again, not intended to be a webinar. Instead, is intended to be a fully live and interactive class. A couple of other things. Kelly will probably go over this again when she gets here, but I will also give a few quick statements here. As I mentioned, as part of this course, you will receive a 1-year license to Altium Designer. Speaking of those videos I was mentioning over here, I do have a walkthrough video here, how to download, install, and set up Altium. Now, everybody registered for the course will get a license for Altium. We highly recommend that you don't use a work email address. So if you registered for the course using your work email address, we highly recommend that you send Kelly, Ivan, and I an alternate email, like a personal email address. We find that just works better. We find a lot of issues with Altium and all the major EDA tools out there, I should say, whether that's Altium, Cadence, Mentor, whoever, that they tend to, when it's a corporate email address, they find the IT department and send all license emails directly to the IT people, even if it's supposed to be for you personally, etc. So just to alleviate any issues we might have is please, we recommend that you send us an email after the fact saying, hey, here's a personal email address I would like to use rather than a corporate one if you used a corporate email address to register for the course. Additionally, after you let Kelly and I and Ivan know what you want to use. If you don't give us a new email address, we will use the one that you register for course with. You will receive an email from Altium, not from IPC, but directly from Altium, with your license and credentials and so on. Please do not register for the trial license. When you go to the Altium webpage, up here, there is a way to go in here and request a trial license. That will have a detrimental impact to our ability to give you these student academic licenses that we're going to be able to give you. So please wait till you receive that email, and I demonstrate what that email looks like over here in this Altium download, install, and setup. So I go through the complete, here's the email you would have received, here's how to follow the link to download, to set up, install, the whole 9 yards. Okay, so you should have that by the end of the week. Additionally, you should also have by the end of the week one of the things Ivan is working on. As part of this course, you also get access to a number of the IPC standards here. So there's a number of them here, and there's a few more that are going to be added by the end of the week that I'm working with Ivan on over here, but there's quite a number of standards. These are all DRM locked, meaning they are going to be node locked to a single computer. So again, whichever computer you download the first one to, whether it's your work computer, your home computer, your laptop, whatever it is, all of the files here will need to be opened on only that one computer. If you made a mistake and you opened one of them at work and you really needed them more at home, again, shoot Kelly, Ivan, and I an email, and Ivan will be able to reset your DRM credentials. You will have 3 months access to this. That is sufficient to 3 months from the start of the course. So 3 months from today, you should have access to these standards, after which you can then go to the IPC store and buy your own copy or have your company buy you a copy, and so on. The last thing with the Altium, starting with this round of courses, actually starting with my previous round of courses, we've also started taking advantage of Altium's cloud service for assignment submission and assignment feedback. Once you have successfully downloaded, installed, and set up your Altium software, then just let me know whichever email address you use that you registered with, and I will add that to our Altium cloud account so that you will then have access to the Altium A365 cloud service there. Now, I've talked a lot about Altium. That is the tool I'm going to be using. I find that as the best tool from a teaching point of view and a demonstration point of view. However, you are free to use any tool of your choosing. You are free to use Cadence or Mentor, KiCad, DipTrace, whatever tool you like. That is absolutely fine, but all of my demonstrations will be using the Altium tool. So with that, are there any questions on that little bit of logistics there? On the, we're going to register you for an Altium account. We should have that to you by the end of the week. If we do not hear from you by the end of the week, you will receive an Altium login based off of whatever email address you use to register for the course. And if it is after the fact, if you would like to use another one, again, just shoot Kelly and I an email. Also, something new we've added, announcements and course forum right here. So this announcements area right here. If I need to give announcements, I'll be putting those here, or forum here. This is where if anybody has any questions, for example, we've seen this in the past where students want to ask questions amongst themselves and they end up trading emails and back and forth. I've instead set up an area right here where any member of the class should be able to go in here, post a question, and other members of the class can reply, as well as myself and Kelly and Ivan can reply. So we have an announcements and a forums area added right here. All right. So please check these regularly and so on. You should also be getting an email that says, hey, a new message was posted to the forum or to the announcements or so on. Any questions on any of this before I get started with today's slide set? Yes, no? No questions?
For us, for example, Edson and I, that we already take the first part of the course, and we have the Altium license and the password for the PDF. Are we going to use the same ones, or we will get
So
new
the
ones?
Altium will be fine. That's your same 1-year license. The DRMs, you will get a new set of credentials because those DRM documents, the standards, they're only unlocked for 3 months from the start of the course. So basically, right, 3 months, that's 12 weeks basically. You spent 6 weeks or 8 weeks in the first course. You've only got a few weeks left before the credentials will stop working. So we give you a new set of credentials each time. So that's where if you find your DRM standards stop working, again, shoot Kelly, Ivan, and I an email. But yes, you will need a new set of credentials for the standards. But as long as if you've already taken the course and you already have your Altium login, that was good for a year. So you should be fine with that.
Okay.
Excellent question, Alonso. Okay. Any other questions? All right. If there's no other questions, then let me jump right into the first set of slides right here. So this course, and I will make a certain statement here, that this course and all of my other courses other than PCB1 assumes you have the knowledge from PCB1. So again, as I commented earlier, if for any reason you feel there's information that you're missing, like I'm talking about topics from PCB1, which is my PCB1 is where I go over schematics, library part creation, and so on and so forth. Schematic symbols, PCB footprints, how to draw schematics, and so on. This class assumes you already have that knowledge. This class also assumes for the project that you had taken my PCB1 and have the project from where you should have been at the end of PCB1. If you did not take my PCB1, and we will look at this on Wednesday, I do have a starting point version of the design that is ready to go that you can just download and start, and therefore you'll have a project exactly where you should have been in PCB1 at the end of PCB1. Okay, with that, let's start here with our slides here. So we're going to start talking about some basic PCB layout, some of the common materials for rigid through holes, a little bit about analog versus digital design approaches, some basics of placement routing techniques and strategies for single and double layer boards. And I say the project you hand out here, we're actually talking about that on Wednesday. Okay. So for the materials, we're going to start right here with the actual board material itself. And when I say the board material, I'm talking about the material of the board layers. We're not going to, we'll talk later on. I have an entire week where I dive into materials in much deeper depth. But for now, what we're talking about is the fiberglass material and so on. So for that, for standard rigid boards, we're going to refer to IPC 4101 for our rigid board materials. And what we're really talking about is sheets of woven reinforcement impregnated with a bonding resin. We will use what are called slash sheets to define specific configuration. Slash sheets in these IPC standards can be thought of just like data sheets for any other component you would go get from DigiKey or Mouser or whoever, whichever manufacturer you get your parts from. They all produce a data sheet that talks about the quantified specific uh, parameters of a particular part. We're going to have the same thing here for the materials. Although there will be a few caveats, and we'll talk about that more in the materials week. Okay. I just want to check something here. Yep. Okay. Describes the mechanical and electrical performance requirements of all materials used in the rigid board. It looks like I got that in there twice for some reason. I'll fix that later. And so what are some of those requirements that we want to worry about with our board materials? So there's going to be some physical requirements such as CTE, the cladding type, the cladding thickness, the dielectric thickness, electrical requirements such as electrical strength and permittivity, and chemical requirements such as glass transition temperature, flame retardant rating, or flammability rating. Note that this is not an exhaustive list. There are many more parameters than just these that are listed here. These are just some of the more common ones that we as designers are going to worry about. So one of the first requirements we're going to worry about is CTE. CTE stands for coefficient of thermal expansion. That's going to describe the rate of change of a dimension of a material due to a change in temperature, right? So this is going to be a parameter that's going to tell us as this material warms up, how much is it going to warp or deform or just expand, right? What's its rate of expansion due to heating, and what's its rate of shrinkage or contraction due to cooling. Okay. It is different in each axis due to the directionality of the fiberglass reinforcement, with the X and Y axis being similar and the Z axis being different. It's typically measured in ppm per degree C and sometimes in percent per degree C. For those out there that aren't familiar with this, ppm, that stands for parts per million, and it is a way of determining the total distance of the change. The percent is a little bit easier, and the XY are going to be similar due to the woven reinforcement materials, the glass or paper or whatever other reinforcement material is used in the layer. That's going to restrain or restrict the ability of the material to expand in that plane. But between each layer, there's only resin, so the resin can expand at a faster rate and therefore have a larger z-axis CTE. Again, we'll talk about all of that in more detail when we get to the materials week. Next, we're going to talk about the cladding type. Cladding, or the bonded metal to the layer. So in our IPC 4101, we have table 1-1, which defines the various different types of cladding, where we have wrought copper, we have rolled copper, we have annealed copper, we have several different types of electrodeposited copper, we have nickel. We can order our material completely unclad, no metal on it at all, just pure hardened material. We can have aluminum. We can have AA bus. So this is one for those that are new to my course. This is a standard terminology used by IPC across all of their standards, and you'll see this AA bus. AA bus stands for as agreed between user and supplier, and it's our catch-all that basically says we don't have a specific requirement here. Whatever you and the supplier agreed to is acceptable, right? So it's our catch-all that says if it's something that doesn't meet any of the other listings on this table, just you and the supplier come up with an agreement of how this will be done, how it'll be defined, and so on, and you can use that there. We also have some specialty things like copper invar copper, an alloy right here, and so on. Now, a quick side tangent note here. I used a couple of terms up here, wrought copper and annealed copper. Does anybody out there know what it means for a metal to be a wrought metal, like wrought iron, wrought copper, wrought, brass or bronze or anything like that? Yes, no?
When those are rolled, it means that those are put it like in a press. that is rolling and pressing
Well,
the
that's the
material?
rolled part of it, but the wrought
Yeah.
part, not so much a press, but a hammer. If you ever see those big hydraulic hammers, or think about what the old school blacksmiths used to do, they take the chunk of iron, get it red hot, put it on the anvil, and beat it with the hammer into shape, right? That's what it means for a metal to be a wrought metal. Wrought metals compress the crystalline lattice structure of the metal very close together. It makes these metals very, very good at withstanding compressive loads, but very poor at tensile loads. So because the crystalline structure is compressed so close together, it's basically like little zipper points, right? So you try to bend it and it snaps and breaks and fractures. But you try to put a compressive load on it because it's already hammered together, it's as compressed as it can get and it does not deform. Annealed copper then. Does anybody have an idea what what it means for a metal to be annealed? Ooh. I got stumped people out there with annealed. Annealed means we've heated and softened the metal. So we basically take the metal to a temperature greater than 1/2 of its melting temperature, hold it there for a duration of time, typically about an hour or so. And what happens is now, instead of the crystal lattice structure being very close together, just like when you go sit in a jacuzzi at the gym or the hotel or whatever, and you all relax and things, all the knots start to loosen up and go away. Same thing here. When you anneal a metal, you soften the metal up by heating it. All the crystalline lattice structure spreads out and relaxes, and now you have a metal that becomes much more malleable or flexible, as very good at tensile or bending loads, but because it's so soft, it's now very poor at compressive loads. So depending on what your needs are, there are some times where you might want to use a wrought copper, sometimes an annealed copper. The most common one we're going to use, though, is this one right here, the electrodeposit, and that's exactly what it says. You have copper ion suspended in a liquid solution. You take the material through the solution, and the copper just deposits itself onto the surface to a given thickness. This is somewhere between, it's not as closely spaced as wrought for the crystalline structure, but it's not as wide out and spread as annealed. But it's the most cost-effective way to add copper to our board. So that's the one we're going to use most often. And there's a bunch of these different treatments, double treated, single treated, high temperature elongation, and so on. So these are just other different properties we can add. Okay, once we've selected what metal we want to use, typically copper here, now we have to worry about how thick of the copper we want to use. And for that, we're going to use table 1-2. Now in table 1-2, we have a designation system here, EQTHM, and then 1 through 14 right here. These numbers here come historically from the from the English weight system. So it's ounces or ounces per square foot. It's really weight per unit area rather than a straight dimensional thickness. So 1 ounce copper really means 1 ounce per square foot. So when you take the density of copper, the weight per square foot, you can determine a thickness. This is how it was traditionally done. Over here, you have a nominal thickness, both in metric and in English right here. Now, note that this nominal thickness that's defined right here is not the actual thickness of copper you're going to get on your board when you get it back from your fabricator. More on that when we get to materials and manufacturing week. But we'll see right here that below about 1/2 ounce right here, even though we have these EQT and so on right here, IPC has now standardized on a actual dimensional statement here in metric. 5 micron, 9 micron, 12 micron. But even those, other than the 12 micron, that's a name, but the actual nominal thickness in micron is somewhat less. 9 micron actually is standardized at 8.5, 5 microns at 5.1, so it could be a little over, a little under, etc. But these are the nominal thicknesses right here for these lower 3 right here as we get into the very thin coppers. Okay. Next, we have the dielectric thickness. Now, those treatments that I talked about a couple of slides ago, and so on, those treatments that I talked about a few minutes ago, one of the things they do is they roughen up the surface of the copper in order to ensure you get good bonding of the copper to the resin, or resin to the copper in this case. Because of this roughening of the surfaces that we talk about here, what we actually have is a minimum, a maximum, and a nominal. Majority of the time, when you see a layer thickness specified for a material thickness, it is minimum. So it's this. So you look at peaks and valleys here from the roughening of the surface right here, and you measure peak to peak, and that is the minimum. The maximum is valley to valley, and the nominal is the average between min and max. And this is due to surface imperfection of the metal spacing is non-uniform in the area of the PCB. Okay, it looks like Kelly has joined us. So I'm going to take a 30-second, actually we'll take a call like a 2-minute breather here. And I will let Kelly come in, and she's out there somewhere. Kelly, say hi, introduce yourself. I already dropped Ivan in your emails in the chat earlier, but please go ahead, introduce yourself to all of our students out there, and then we'll keep up. Kelly, are you out there? Is your mic working?
I am out here. Good morning, good afternoon, or good evening, wherever you are located. Welcome to Chris's class today. As Chris mentioned, I am your IPC support in conjunction with Ivan Santa Cruz. Feel free to email either Ivan or myself if you are having any difficulties, if you can't find something located in the classroom. Later on this week, you'll be receiving information regarding DRM access, as well as Altium access, which I'm sure Chris is going to go over if he hasn't already. You'll be receiving that information from us, and we'll communicate to you when it is available. And if you haven't received it, you can communicate with us and let us know. Please feel free to communicate directly to Chris if there is anything regarding course content. You can also let us know in the classroom by responding via the chat, or raise your hand or come off mute if you have any questions. Chris is also very welcoming for class questions, so please don't hesitate to either drop it in the chat or raise your hand to bring your question to his attention. I will also say, just as a small side note, today is Chris's birthday, so happy birthday, Chris.
Thanks,
And
Kelly.
I hope everyone has a wonderful class. Thank you.
All right, thanks, Kelly. And yes, we already talked Altium, and I dropped you guys' emails in there. We went over all the stuff, but thank you. Thanks, Kelly, for introducing yourself. All right, with that, let us keep going here. So we talked about material dielectric thicknesses right here. The next is going to be the electrical strength. Electrical strength describes the electrical insulative property of the material, and it's going to be defined in volts per unit length. Again, to this week, I'm doing a fairly high-level introduction to some of these properties. We're going to get into those in a lot more detail when we get to the materials week and the manufacturing week. But again, we want to have a way to describe how much voltage over what distance the material can insulate against. Then we have permittivity. Now, for those out there that are in the engineering side of things that went through engineering degrees, we talked permittivity. For those that went through the technician side, we talked about dielectric constant. This is one that I still see confusing people occasionally out there. They are the exact same thing. Relative permittivity, or epsilon sub r, and dielectric constant, or d sub k, are the exact same parameter. It just depends on which curriculum and which group of people you're talking to. If you're talking to a room full of engineers, you talk in terms of permittivity. If you're talking to a room full of designers or technicians, or manufacturing types, you talk dielectric constant. They are the exact same. Now, it is a parameter that's used in the calculation of a transmission line characteristic impedance. It's used to define signal propagation on a transmission line, and it varies with resin content in a particular system. We'll also talk about a few more of these properties right here, and I've got a second slide on relative permittivity or dielectric constant right here. As I said, this is going to affect our impedance and our wave velocity. It's going to vary with three different conditions here: with the test frequency, or the frequency you're running at, the resin content, which is the percent of the layer that is the epoxy or resin and not the glass or reinforcement, as well as the construction of the layer. And technically, resin content and construction, we'll see later, do go hand in hand. It is possible to have a large variance in resin content and relative permittivity for a given material thickness, even within the same resin system. And we will again see this moving forward here in a little bit. Therefore, we should always spec the thickness and construction for each layer. We'll look at an example of properties files later on. We'll skip that today. Now, I'll put a caveat here. I will put a caveat here that says may also spec right. So I'll put the asterisk there. So basically what I'm saying here is, historically, I have always said, and this is still the way I do it in all of my designs, is I say, I want Isola 370HR for this layer, and I want it to be 2 sheets of 106 construction here, and so on, to get my 5 mils or whatever I need. Okay? Now, I do that because I've already gone through and calculated all the parameters I need, and I know that that will work for me. For those individuals that work in organizations where that is frowned upon to spec a specific material, that instead you're supposed to, whether for DFARS here in the state or other procurement activities, supposed to allow vendors to quote their recommended. In that case, it is acceptable to go in and say, okay, well, I need this layer to be 5 mils thick, have a resin content of a minimum of 60% and a dielectric constant of a maximum, between 3.5 and 3.6 for the dielectric constant. So basically, you can do the exact same thing that you get away with thickness and construction by also saying, here are the properties you need to meet. As long as you meet all of these properties, then you can recommend the material you want, and so on. And we'll talk about that again later on when we get to materials week. Okay. Glass transition temperature. This is the temperature at which the resin changes from a solid into a viscous gel. The material properties are going to be different below and above the T sub G value, and T sub G is simply an extrapolation of the linear regions of the curve. Again, more on this when we get to the actual materials week, but effectively what we're saying here is, below this T sub G value, I have a very large change in temperature, gives me a very small change in material thickness. Above T sub G, a very small change in temperature gives me a very large change in material thickness. Okay? But you'll notice I have a fairly linear region here. I have a somewhat linear region here. I take those two linear regions, I extrapolate, and that's the temperature I define as T sub G. T sub G is not a step function. It is not a light switch, an immediate on or off, where you can sit there, and I have had many an engineer in my career tell me, oh, I'm 5 degrees under T sub G, I should be fine. And it's no, you're not. You want to stay out of this nonlinear region. This is where lots of bad things happen to your board. So we'll talk about this later in materials, but I always recommend, IPC does not have a explicitly stated recommendation, but my 30 plus years of experience have said I always try to maintain about a 50 degree C delta between my maximum expected operating temperature of my board and the T sub G material for the board. So I try to keep my board always operating down here in the linear region below T sub G. Okay, so more on that when we get to materials. Loss tangent or dissipation factor. The official scientific definition for the dissipation factor or loss tangent is the ratio of total power loss in the material to the IR product of a capacitor made of the same dielectric material. That is a very clunky, cumbersome physicist way of trying to define this behavior. The way I always explain it is the following. The higher the loss tangent, the more energy is lost in the material, and therefore the slower the signal must be in order to successfully travel down the material. Meaning, and we'll get into, I don't get into it in this class, but in my RF classes, we get into this concept of skin effect, that at higher and higher frequencies, the energy of that signal is now out at the surface of the copper trace, and very little of the energy of that signal is in the core of the trace, and therefore it's in contact with the surrounding material. If the material has a high loss tangent, then it acts like an attenuator, and all of that energy gets dissipated in the surrounding material. Therefore, if you run at slower frequency, now your energy is interior to the trace, and therefore it can travel down basically travel down the trace without having too much of it attenuated in the surrounding material. Loss tangent or dissipation factor is going to vary with frequency, resin content, but now it's also going to vary with temperature and humidity. Because this is a dissipation or a dampening effect, just like you have with other spring forces, the softer or more malleable I make the surrounding material, the higher its dampening factor is going to be, and the more energy is going to be lost. So if I allow the material to get very soft, either from temperature or humidity, moisture absorption, the softer that board material becomes, the more energy is lost to the board material. Then we have the flammability rating. This is from the standard UL 94. And yes, for those here in the States, UL, Underwriters Laboratory, the same Underwriters Laboratory that puts the white tags on everything you have ever bought at a store, whether it's a little desk fan, a microwave oven, a pillow, a blanket, or whatever. Everything nowadays has a UL tag on it. Well, UL has a test mechanism called a flammability rating. It's UL 94. They take a specimen of the material, they put it in the rig here, and they start flicking a flame at it, kind of like a Bic lighter, but more controlled. And they test how long it takes to self-extinguish. And there's a question popped up here. Not a question. Someone has to sign off. Check the recording later. Yes, that is a great point. As I had mentioned at the very beginning, but since someone is already taking advantage of that, since these sessions are recorded, if for any reason you have to show up late or leave early, by all means feel free. You can always come back and check the recording. Typically, it's the next business day. So typically by close of business of the following business day, usually by noon of the following business day, but worst case, close of business following business day, we will have the recordings posted into the Edge page. And therefore, if you do have, for any reasons, need to miss a class or show up late or anything like that, it is not a problem. You can always watch the recordings later. All right, that being said, we will go over here. UL 94 has three primary ratings that we are going to be concerned with for boards, and these are the vertical burn rating or the vertical burning test. We put a specimen of the material in our apparatus here. We apply a flame to it. V0 is going to be our best rating, so the lower the V number, the best rating we're going to get. It says the material must self-extinguish within 10 seconds of each flame, 50 seconds after 10 flames with no dripping particles and no glowing combustion, 30 seconds after the second flame. V1 is a little bit worse. We're now 30 seconds of each flame, 250 after 10 flames, no dripping particles, no glowing combustion, 60 seconds after second flame. And V2 is a little bit worse. It's the same times as V1, but now allows for some dripping particles. If your material is lower quality material and cannot pass any of the V rating, there is a second one, which is the HB or the horizontal burning, which is rather than putting the specimen in vertically here, they put the specimen in horizontally. So you're putting a flame over a smaller area rather than letting it climb up the material here. Okay. So again, this is the V rating. And again, if you're working in, say, a high reliability market, such as medical, military, aerospace, anything like that, you'll want to go for a V0. If you're working in consumer goods or freebie giveaway swag, you might be willing to go to a V1 or a V2 to get the lower cost material. Now, the material itself, FR4. How many of you out there in your careers over time have gone to a fabricator and say, please make my board out of FR4 material? Yes? No? Oh.
Yes, Chris. Absolutely, you're right. FR4 is the most useful for double layer and multi-layer.
Yeah, FR4 is not a material spec. And that's what we're going to talk about right here. So, what FR4 actually stands for is flame resistance or flame retardant grade 4. What we mean when we tell a fabricator FR4 is we're asking for an epoxy-based resin with a woven glass reinforcement with a flame retardant mechanism added to the resin. FR4 was originally a rating system developed by NEMA. It goes hand in hand with the UL94 flammability rating. And there are actually many different formulations with many different electrical properties that all meet the flammability rating of, or the flame retardancy rating of FR4. From IPC's point of view, it is not an actual material spec. However, it is used in industry as a standard term, as you just heard Edson say. What we actually need to spec is the IPC slash sheet for the specific formulation desired. And that's what these are right here. These are going to be our slash sheets. So our slash sheets right here, these kind of look like a data sheet. And what these are going to contain is they're going to contain a header and information up here at the top. This will describe the resin system, what type of epoxy it is, what type of TG it has, whether or not it's FR4 rated, what it's what's the word I'm looking for here? The primary and secondary resin right here. So is it a multifunctional epoxy, bifunctional, difunctional? Is it a phenolic resin? Is it cyanate ester resin, right? What is the resin system? Is it woven E-glass, woven S-glass, phenolic paper, et cetera, et cetera? It's RoHS compliant bromine as its flame retardant mechanism. So this describes the resin system as a whole. And then you get into the quantified areas of data right here. Peel strength, volume resistivity, surface resistivity, moisture absorption rates, permeativity, loss, tangent, so on. Now, one thing to note with the IPC slash sheets. These are a minimum acceptable level, meaning as long as the material meets or exceeds these values, the material can rate itself to the slash sheet here. So this one happens to be slash 126. And we'll go over that in a lot more detail when we get to materials week. But what I have seen happen many a time by designers out there who at least know the IPC slash sheet system, they go pick the slash sheet and then they just use the values off of here. Well, the values off of here say your permeativity needs to be, worst case, 5.4. Well, there's many slash 126 rated materials whose permeativities are in the like 3.5, 3.6, 3.8 type of numbers that are way below this, and you'll get a vastly differing electrical performance. So we'll see all that when we get to signal integrity as well as other behaviors here. Okay, but I want to point these out that at least we have the starting point for the minimum acceptable quantified values here, as well as describing the resin system right here. Okay. All right. Perfect timing right there. So that got through the high level introduction to the materials. This sounds like a perfect place to take a break. Why don't we take like about 14 minutes, take a caffeine break, bio break, be back at 10 minutes after the hour. And one other thing, almost always with very few exceptions, I stay online during the breaks. If anybody has any questions they would like to ask, comments, questions, observations, anything of that nature, feel free. I will stay online. But otherwise, 14 minutes, 13 minutes now. Caffeine break, bio break. Be back at 10 minutes after the hour. All right. And then we'll pick up there with digital and analog design approaches.
Hey Chris, this is Brian.
Hey, Brian.
Um, do you want us to email you our email associated with our Altium account so that you can add us to the cloud, or how do you want that information passed to you?
So if you already have a your own email, or sorry, your own Altium account already, then yes, just
Okay.
send Kelly and I that email and say, hey, I already have an existing Altium license. Here's the
Okay.
email address that it's registered with. Now the thing is, so we'll add you to our cloud if you're already using a cloud account at your employer or wherever. You'll just have to sign out of that cloud and sign into the IPC cloud each time. I'm sure you know how to do that. Yeah.
Yeah. Yeah. Do you have that? Do you send the IPC cloud information then, or?
It'll just show up.
Oh,
Literally.
okay. Okay.
Literally, once I've added you, as long as you have an existing, you know, Altium account, the next time you log in, if you pull the little pull down where the the little cloud globe thing
Yeah.
is, right? You'll see,
Mm-hmm.
oh, there's a second one I can connect to here. So yeah, there's just nothing
Okay.
to send. It literally just shows up in your Altium.
Okay. And then I didn't take the first course, so I don't have the project that we're starting with.
We're gonna get to
Okay.
that on Wednesday.
Okay.
I just turned off my share, but I will turn it back on here in a
Oh, you
moment.
don't. Okay.
Literally right here inside of the class. Right here, I have a start point project. You literally download as a zipped up packaged project
Okay.
of where you should have been at the end of course one. So don't
Okay.
even worry about it. Do not stress about it at all.
Okay, because I think my week one looks a little different. I don't know if maybe now that we started the course it'll
Yeah, that's because as
change.
an instructor, I've got all the stuff that's hidden
Okay.
from the student. You should see
Okay,
week
that
one
makes
assignment, start point project, and start point project asked for
yeah.
right here. Right.
Yeah.
Yeah. Any of
Okay.
these ones that you see the little blue bars on, yeah, I'm teacher. I get all the hidden stuff. You
Okay.
guys, the students, you don't get my hidden stuff. That's for me.
Okay. And on the syllabus it said there was no week one assignment, but it shows one here. Is that just kind of
The
a
week one
supplemental?
assignment, there's no official, basically week one assignment is go get the project, download it, and just open it.
Okay.
There's
Okay.
nothing to do. Yeah,
Okay.
that's why there's no official week one. Week one is, yeah, here's the project. Make sure. Basically, because week one is always, did you get Altium installed? Did you run into any problems? Did we get you
Right.
added to the cloud, et cetera, et cetera.
Uh-huh.
So week one always ends up being, when I teach like
Yeah, kind of
software
a
classes at university, it's the equivalent of Hello World, right? In hardware
yeah.
classes, it's always make the LED blink, right? It's
Yeah.
the exact same thing. Or it's basically, is everything working, right? So
Yeah.
that's all week one is.
Okay. And then there is going to be one week I'm going to have to miss both
Yeah,
lectures,
yeah,
but
that's fine.
I can just
They'll
catch.
be
Yeah, I can
recorded.
just
Yeah,
catch. Okay.
yep, there'll be a
Perfect.
recording. Hmm.
All right. I think that's all I got. Thank you.
All right, no problem. Okay, is everybody back from break? Yes, everybody out there back from break?
Yeah, I'm
here.
back.
Excellent. All
And ha-
right.
and
Let's
happy birthday.
thank you, appreciate it. All right. Moving on, let's start talking a little bit about analog versus digital design approaches. So care must be taken when designing different types of layouts. For digital signals, care must be taken of the signal timing and signal integrity. And for analog signals, care must be taken to ensure current and power requirements are met. Care must be taken to minimize noise in the signal. More on all of that here coming up in a little bit, as well as throughout the course. For analog signals, our main goal is to minimize the signal path and to keep the signal away from, quote, noisy digital signals. We often want to use dedicated return path and power path back to the actual power source rather than a shared path, uh, if that's feasible. Component placement within the functional block is going to be very critical for analog signals. And we want to avoid loop areas, and we want to use short straight paths whenever possible. Duplicate slide again. My bad. For digital signals, on the other hand, we want to be more concerned with our signal timing requirements. Signal integrity must be analyzed, and transition electrical length is needed to determine the requirement for reflections. Placement is going to be less critical than signal integrity or signal timing. We're here. Yes. Yes, Kelly has a great point in the chat. I know some of you were just already talking about sending some emails. I do teach 5 different classes for IPC, and Kelly and Ivan manage even more than that. Please do us a favor whenever you send an email to us to please include the class name as well as quarter. So like this is PCB2 quarter 4 of 23, right? Because what ends up happening is we get so many students that say, "Oh, I was in class last night and need X, Y, Z," and we're like, "Which class were you in?" kind of thing. So, yes, please do us a favor, as Kelly just mentioned in the chat window. Whenever you're sending email communications, please include the class name and course, quarter, and so on, so that we can more easily help you guys out. All right. Back to digital design approach. Signal integrity and signal timing is going to be very critical. Component placement, not as critical. We're going to see that with digital, the placement of the parts is not going to be near as critical as they would for analog. Okay? So taking a look at a digital example right here. I like this one here, and that right here, this is one that not a lot of designers right here, where there's all these squiggles in the line. How many of you out there have ever opened up a board for a product? I don't know, memory cards for your desktop computers, whatever, video cards, anything like that. Open them up and seen a designer that did something like this, where you have all of these squiggle lines in the traces. Yes, no? How many of you out there have seen that? Right? Okay. Now the question is, does anybody out there know why we put the squiggles in the line like this?
Too much the length.
What's that? What was that, Alonzo?
Too much the length.
Yes, exactly. What we're looking at here is we're trying to follow the total length, say from point A right here to point B right here. And we're taking a look at all of these, and what we're trying to do, and this is only showing the top layer, so obviously these are going to a via and going somewhere else internal. But what we're effectively trying to do is make the entire path length, say a 32-bit or a 64-bit data bus or whatever the case is right here. We want that all 32 or 64 bits, each one has their own line, and we want the total length of each line to be exactly the same length, so that the signal, when I change from a 0 to a 1, say I write a new set of data, that all the data enters here and leaves here at exactly the same time. Because if I have a significant difference in the length here, the data bit on this line may get to the destination much faster than the data bit on this line, or vice versa. So we're doing this in order to match the length, in order to match the timing, so that the timing, our digital timing, is more accurate. For single layer boards, this is a much more critical. For any of you out there that are still designing in very simple single layer boards, care must be taken during placement to allow for all routing channels. We'll use a combination of component rotation and placement to optimize the routing. For through-hole designs, we want to ensure that the pad-to-pad clearance allows for a trace to route between the pads, and alternatively, we can use what's called a dog bone to allow the trace between the pads. So first we'll look at dog boning right here. So let's assume that this red layer right here, everything needs to be routed on the red layer, and let's also assume that we can see that there's a trace that's going to be up here and a trace that's going to be down here. So I can't go down, through, and around up here. I have to go, down, over, and back up. I have to go through. Let's also assume that we have calculated we need this 25 mil wide trace right here. What we end up with is we see the clearance boundary right here that says the copper to copper of these two gray pads with the width of this 25 mil trace here is not sufficient to allow a 25 mil trace to get between those two pads and still meet our various clearance rules. So what we will do instead is, for a narrow length, we will shorten or narrow the width of the trace sufficient that it can get between the two pads right here, and then we'll immediately go back up to the wider trace once we get outside of it over here. And so on. So by doing this, narrowing the trace for a short distance to maintain the required clearance between the copper features. Now, I've been asked many times, doesn't this violate the current or the temperature rise? It does, but only for a short distance. So what you end up, if you've calculated, say, a 10°C rise above ambient using 25 mil trace, for this one short area, you might see a 15 or 20°C rise, but then that thermal energy will then be dissipated back into the wide trace right here, back to where it needs to go. So as long as we don't go down to a width where we'd end up having a fusing condition based off of the current in the trace, we are absolutely fine to do something like this here. Okay. Again, I just went through, I spoke in words what I have in slides here. The nominal 25 mil trace cannot route through the pads. Reduce the trace width to route through the pads right here, and so on. And so that's the idea of our dog boning right here. That's one technique when we're dealing with single light. Right, we'll get to more single-sided here in a moment. We talked about the serpentine routing in our digital traces right here, but from a placement point of view right here. We'll see us here in a minute here. With our analog, we're going to be very particular about how close our parts are to each other in our op-amp circuit, in whatever kind of circuit we're working on. With digital circuits right here, I've got my big FPGA up here. I've got some Ethernet and USB ports down here, and there are various different controls and chips and so on here. But you'll notice they're just kind of roughly placed here. Kind of everything's kind of lined up here. Because again, what I really care about is, A, do I give myself enough room here where the alignment and the placement's not critical, but I care about the timing, so I've got enough room to put the squiggle lines in there for the serpentining or the routing channels right there. And so the desire is for length and signal tuning rather than for ultra tight placement of parts to each other. Okay. For single and double side boards for analog circuitry, trace width is going to be defined by the current, and the trace clearance is going to be defined by voltage. So in our IPC 2221 standard, we have table 6-1. So in section 6, which is our electrical performance section of 2221, we have a chart here called table 6-1. The chart has separate sections, with section B being for bare printed wiring boards and internal layers, and section A for CCA assemblies. Now, this is broken down into 7 columns. We have column B1, B2, B3, B4, and then A5, A6, and A7. So 7 columns. The first 4 are B, the last 3 are A. And the way this chart is going to work is we also have rows right here, which are voltages. But, and for those that are out there as engineers, read the table carefully. It says voltage between conductors, either DC voltage or AC peak. Be sure to convert your RMS voltages to peak voltages before using this chart. Otherwise, you can get yourself into a little bit of trouble. Again, all of us that have studied electrical engineering, we typically use RMS voltage when we're describing like the 120 volts coming out of our outlets, you know, and our walls at home and so on. That where we say it's 120 volt AC, it's really 120 volts RMS. It's closer to 170 volts peak voltage right here. So we want to look at the voltage, and all we're looking at is the total voltage, worst case, between 2 points. Now, some other safety chart systems out there like CSA and UL allow for linear interpolation. IPC does not. These are step functions here. If I am even 1 volt over my 30, I have to use the next row right here and so on. So if my total delta V between 2 points is between 0 and 15, I use the values in row 1, 16 to 30 row 2, and so on, all the way up to 500. Above 500, we'll talk about this later. There's actually a formula to calculate what the total clearances you'll need. But for now, we're going to stick at the 0 to 500 volts right here. And then we'll look at our columns right here. B1 column is going to be used for all internal layers. Columns B2 and B3 are used for all uncoated boards based on altitude the board will see, with B2 being sea level to 10,000 feet and B3 being above 10,000 feet. Now, when we say uncoated here for bare boards, we're talking about solder mask. If any of you are out there remember old boards from like the 60s, 70s, even the 80s, and even partway into the 90s, boards did not always have solder mask coating. Oftentimes, boards were just, after the etching, they were just dipped in molten solder and had the excess blown off, and that was the surface protectant. Okay, so if you have an uncoated board, you can use the B2 and the B3 for your external layer clearances. The B4 is for all boards containing solder mask. Now, when we say bare boards, what we really mean here is there's certain cases of RF boards where all of the features on the board are actually etched in copper geometry. There's no actual part soldered in. Or we can also use the columns B2, 3, and 4 if we need to have tighter routing. For example, I have, and going back up here, we'll look at a picture here. So I could argue that I could use the B columns right here where it's just trace to trace, where I don't have exposed solder pad, so I don't have opening in the solder mask. So I could make the argument that I need a slightly larger clearance here where the trace goes into the individual pad. But if I'm really fighting for, you know, every last bit of room on my board because I'm very high density, I could make the argument that I can use the B2, 3, or 4 column for the trace to trace clearance rule, and then the A column for the pad to pad clearance rule because of the with or without the solder mask coating and so on. Okay. Then we get into the A sections. The A sections of the chart have 3 options. A5 is used for boards with SMT only and assumes conformal coating and any elevation. A6 is going to be through hole and surface mount without conformal coating, sea level to 10,000 feet, and A7 through hole and surface mount with conformal coating, any elevation. So most of our assemblies, we're going to assume that there's going to be a conformal coating on them. And so we'll use either the A5 or the A7. Now, there is some contention even amongst the IPC committee members who wrote this standard. And we'll see that later when we get to the manufacturing weeks. But we'll see that later, that the actual language of the definition between A5 and then the A6 and A7 can be used, the argument can be made for the A5 being surface mount only. Others have argued that A5 is RF with conformal coat only. That's only the conductor area, but not the solder pad area. So there's a little contention, and we'll go over that in a little more detail. But this is the definition that's the most widely accepted. So this is the one we will use right here. Once you determine the coating and the elevation requirements, you need to determine the voltage between the conductors. We'll select the row that has your voltage and the column that has the coding and elevation needs to determine the necessary spacing. As an example here, if we were to select 160 volt DC of a mixed through hole and surface mount assembly with conformal coating up to 40,000 feet. Well, 160 volts is our total delta. It's right here between 151 and 170. And because we are with conformal coating above 10,000 feet and mix of through hole and surface mount, we're going to go to A7 column right here. Using that, we'll see that we need 0.4 millimeters or 16 mils as our clearance on the outer layer for those copper features. Okay, so we're simply going to use this table over and over and over again based off of the design itself. Okay. Okay. Back to our analog single layer routing. We're going to use short straight paths, place parts as close as possible, place decoupling caps close to the power pins, and you may need to route in slight loops to use a single layer. I highly recommend you try to avoid single layer boards whenever possible. I know it's not always achievable, but with modern designs, reality is that if you order a single layer board nowadays, the fabricator is selling you a double layer board and just etching all the copper off of one layer. So you pretty much get double-sided boards for free regardless. So I would recommend taking advantage of that. But we'll take a look here at how we would do this. So for those coming back from PCB1, you might recognize this as the pressure transducer signal conditioning circuit right here, instrumentation amp circuit right here. Here it is laid out and fully routed in single layer mode. So everything has to be routed on the top. There's no opportunity to use vias or to place parts on the bottom side. And so this is the best that we can do. We have relatively short and straight paths, but we have some less than optimal, such as right here I have to go up and over, and then down here I have to go down through the pad, up and over here, and then back up to here. Again, through the center between the pads, I might have a solder bridge there if the solder mask is misregistered, and so on. And the worst case condition right here. Let's take a look at this signal right here. So I've got a trace. It goes from this pad right here, goes up here to this point. From this point, it goes up here, and it splits again. One side goes over here. The other side goes here, and then here, and then here. Can anybody tell me what this copper structure kind of looks like to you right here? Ooh, nobody has a guess of what kind of free structure I've just made by routing in this weird meandering path like this, splitting it and going in two different directions.
Like an antenna.
Yes, absolutely. We've made ourselves a free little dipole, almost a tripole antenna here, actually. If we go from this point right here, we've got one pole wraps around this way, one wraps around this way, and then this kind of wraps and squirrels up here. But yes, we have just made a free antenna out of our board. And then people who do this kind of stuff, and then they wonder why their board picks up all kind of RF and has all kind of weird noise every time they're using it, and they feel they have to keep putting caps, more and more caps on the board. Plus, we'll also note here that, for example, our two decoupling caps right here. The power pins are here and here, but yet I had to put the caps down here because this trace had to route out the side over here. Now I could get in was going inside like that. So again, this works. It also takes up quite a bit more board area. If you just visualize, how much area this is here, roughly, we can see that while it's achievable, it's less than optimal. You do get these free antenna structures right here. They can become both not just susceptible surfaces picking up, but they can also become radiating surfaces. Any energy, any signals on those traces can start radiating out. So this can be also an RF generator, not just an RF receiver here. Okay, now, same exact analog circuit, but now using double-sided placement and routing. Number one, you can visually, I hope you can visualize that this is taking up significantly less area of my board. Other than the 3 test points right here and the IC chip, all the other surface mount components have been placed on the bottom side of the board using up what I call the dead space, the z-axis dead space. Basically, since I'm not going to put a via right in the solder pad right here, basically all the area underneath the surface mount pads right there, I can place the surface mount R's and C's on the bottom side. And therefore now, instead of that long squiggling path to make those ground connections, now instead, I have this short straight path right here, out via and back in, out via back in, and so on. So you can see my path has gotten significantly shorter and straighter path simply by taking advantage of the double side placement and double side routing. Shorter paths, optimal paths. However, the drawback, the caveat right here, is we did have to use vias. So we've added vias to design. This one up here, there's no vias, so no drilling and plating of our holes. Right, so again, it's a 6 of one, half dozen of the other kind of thing. The via design and manufacture has become so ubiquitous and so commonplace nowadays that it's no longer the problem it used to be when they were first being developed, so should not be an issue. Okay, speaking of vias, we need to know how to design the via. So in order to meet the current carrying needs, the via minimum size should be designed to have the same cross-sectional area as the trace they are connected to. Assuming that T, whether T1 or T2, is small with respect to W, the via size can be approximated as W over 3. The full equation right here for D2, the inside diameter of the via, based off of a width, assuming we've already sized our trace width to handle the current we want, the via to handle the same current would be the size D2 is the W divided by pi multiplied by T1 over T2 minus T2, right? Now T1, the surface copper thickness, is typically about twice T2 right here. T2 is pure plating, T1 is surface copper plus plating. So we will typically have T1 over T2, so maybe let's say that's 2 over 1 is 2, minus 1 is 1. So this whole term here goes to 1. So we end up with W over pi, which can be simply reduced to approximate it as W over 3. W over 3 is going to be slightly larger than W over pi, therefore should be sufficient. That is a good first order approximation. Okay. Now note, my graphic right here, when I had my graphic designers create this slide for me, this is not intended to be that this is a blind via here. This was simply in order to have the red and the black text here show up with high contrast. I just had her go only part way through so that the text right here was against the green background of my board. But whether it's a blind via, a buried via, a micro via, or a full through via, the math works out exactly the same. What we're really trying to do is get the cross-sectional area of just the copper of the barrel wall right here to equal the cross-sectional area of my trace right here and go from there. Now, we do need to consider manufacturing limits when sizing vias. The number one manufacturing limit we are going to consider is the aspect ratio. Aspect ratio is the ratio of the board's thickness to the hole size. Most fabricators, especially here in the States, have a typical value of 10 to 1 max for standard fabrication. They are willing to go larger than that, 15 to 1, 20 to 1, and so on. But those are going to be either advanced or emerging engineering technology, and you're going to be looking at higher costs because of higher scrap rates and much lower yields. So we want to minimize that. So, and where I'm going with this before we talk about the next two bullet points here is, if you have a lower current trace, something to say like carrying an amp or 10 milliamps or 100 milliamps or something like that, right? Your math might say that you only need a via that's, 4 mils or 3 mils in diameter. But if your fabricator says that's mildly interesting, the smallest possible hole I can put in this board is 10 mils or 15 mils because of this aspect ratio, well then you're going to end up using the larger via, and you're just going to have oversized, and you're going to have margin. So we always want to use the minimum practical via size. And for higher current needs, you may use multiple vias in parallel instead of one overly large single via. Okay? Research shows that multiple parallel small vias have the exact same thermal and current carrying capacity as a single large via, so long as the total cross-sectional areas are the same. So meaning, if I calculate that I should have a via whose hole is 50 mils and pad is 70 or 80 mils, that is an overly large hole and not very easy to use. But instead of one 50 mil hole via, I could use 5 10 mil hole vias and get the same cross-sectional area. So as long as my cross-sectional area of multiple vias in parallel is equal to or greater than the cross-sectional area of the trace, then I'm absolutely fine using multiple vias in parallel. Okay? Via pad sizing. For the via pad sizing, we will follow the same IPC class size requirements for minimum annular ring, with being 1 mil for internal layers, 2 mil for external layers for class 1 and 2 in IPC 2221A or older. Starting in 2222, all of them were 2 mils for external layers. And so on. They just upped it and said, yeah, it's easier. The 1 mil was problematic for the fabricators. And then we'll follow the same manufacturing tolerance analysis used in footprint design to ensure the minimum annular ring size is met. I will also show you in producibility levels in the IPC 2221 and 2222 how we can actually do our pad sizing. Okay. All right. Now let's talk about digital traces for a moment. Actually, before I move on to digital traces, any questions on the via sizing? Okay.
When you measure the via, do you have to approach the hole to like a standard tool to make the hole?
No, you are the designer. You are designing the hole to whatever size hole you want. It's up to the fabricator to fabricate to your design.
Yeah, but for example, when we are tooling metal pieces, we have to approach the holes to a tool so it will get cheaper. It's not that expensive to have like a 0.002 hole and the tool is 0.0021.
Right. So there are standard drill sizes, but because of the plating process right here, the fabricator always drills their hole larger than your designed hole. So it's up to the fabricator to deal with that. And they have, I don't want to say an infinite, but I believe it's like about every half mil of size, both between the metric and the English sizes and tolerances. So no, you don't have to worry about standard tool sizes. All you as a designer have to worry about is this aspect ratio and your plating allowances here. And again, so Alonso, it sounds like you did not take my PCB1, correct?
Yeah, I take it.
You took it. Remember the discussion then in week 2 when we were doing the library about how to go through that tolerance analysis of, once you had the pin size, then the hole size and the plating allowance and the fabrication allowance. Remember all that in week 2 of PCB1?
Yep.
It's the same thing here, except now because we're not soldering, we don't have to worry about the solder working in a pin. So, well, here's the hole size I want. Here's what my fabricator allowance is. Here's what my plating allowances, my fabrication allowance, my designer's hole size allowance, and so on. Use all those, come up with what your finished hole size needs to be, and once you've got your finished hole size, now the one thing I would recommend is you don't have to worry about a standard tool size, but I would round up to like the closest 1 mil, right? Like, don't put on your drawing that you want a 4.792635 mil diameter hole, right? Then your fabricator is going to get a little annoyed at you, okay? If you come out with 4.79 for your hole size, just make it a 5 mil hole, right? Kind of thing. So just round up to the nearest single mil, but no, you do not have to worry about standard tool sizes. The cost is negligible, if not already zero on those, and you'll see why that is here moving forward when we get to the manufacturing week.
Okay.
All right. Great question though. Okay. Any other questions on vias before I move on? Okay. So all traces on a printed wiring board behave as transmission lines. Now this is one, we'll get into this in much more detail when I get to my signal integrity discussion. But to start with here, this is one that blows a lot of people's minds. Okay, because of the way we learn electrical engineering in university, and because of the way up until the last 10 or 20 years or so, because of the way we've always learned to do boards in the past, silicon and signals were so slow that it did not matter. We didn't have to consider that. But the reality is that everything flows in a loop, and that loop flows in what's called a transmission line, which is not only a physical trace out, but also a return path back. So because of that, because we're going to design for transmission lines, for digital, we need to have controlled impedance transmission lines. There are 4 physical parameters used to define the impedance. And those 4 physical parameters are the trace width, the trace thickness, the height of the trace above the return or the mirror plane, and the dielectric constant of the laminate material. So looking at a surface layer, what we call a microstrip right here, we'll see those 4 right here. Width, thickness, height of the trace above the return, and the dielectric constant right here. There's a first order approximation equation right here for a surface microstrip. It's 87 divided by root epsilon sub r plus 1.41 times the natural logarithm of 5.98 times h times 0.8 times w plus t right here. And so we have all those. Now, with this one here, with all these first order approximation equations that you see in IPC, there's usually some limitations on those. The surface microstrip typically tends to only be valid between about 5 and 15 mils, too narrow or too wide, and the equation starts to have some error introduced and some uncertainty. Also, this is only valid when W over H is less than 1. We recommend that you use a 2D field solver software for a more accurate calculation. In fact, the transmission line calculator, controlled impedance calculator in Altium is now a fully licensed 2D field solver that has been quite successful. Also, my recommendation, your fab house is your friend. Consult your fab house. After you develop your stack up and you characterize your impedances, have your fab house verify them that A, your assumptions are correct, and B, that you meet their manufacturing capability, right? So the fab houses have some statistical process controls in place where they know based off of their laminate press and press temperature and etching and cleaning and all that, how these numbers are going to differ from the nominal numbers when the material first comes in. So having your fabricator tweak your stack ups to meet their process will help you to have boards that are completely successful the first time through. Okay. Generally accepted formulas for impedance related calculations originally came from IPC D317. Again, now we're including IPC 2221. And so you can see there's the Z naught. There's also a C naught if you want to calculate the characteristic capacitance right here for the surface microstrip. Then we have the next structure right here, which is called the strip line right here. Sorry, can't talk now. We have the controlled impedance right here for what's called the strip line. This is a single signal layer on internal where I have a plane, a reference plane, both above and below. And so now you can see I've got the thickness here, but I've got 2 different values of H right here. Now this is symmetrical, so H is the same, but I've got 2 H's right here plus a T. And you can see I've got a slightly different equation for Z naught and C naught right here. Then we have the dual strip line right here, where I have 2 signals sandwiched between 2 planes. This is probably going to be the second most common structure, this one in surface microstrip, that you will use. We'll see why that is right there. That's typically because we can put 2 signal layers, with one being primarily horizontal, one being primarily vertical, and therefore they won't interact negatively with each other, but they can be sandwiched between them, and we save a few layers right there. And so again, more complex Z naught and C naught equations right here. And then finally we have the embedded microstrip. This is where if you do 2 signal layers on the outer surface before the first plane, first one is completely exposed to the environment, and the other one is embedded in the dielectric material, but does not have a reference plane above. And you get this equation right here. Again, much more complex version of the equation right here. Tools such as the Saturn PCB toolkit, which I have a link to on our Edge page, as well as tools like what's built into Altium, will solve the impedances, currents, temperature rises, and other parameters and traces. Note that the Saturn PCB toolkit right here, okay. Note that the Saturn PCB toolkit right here claims that they developed their own equations for impedance that are still an algebraic formulation rather than a full 2D field solver. It's not the simplified ones in IPC, but it is not a full 2D field solver. And they claim that it tracks the results of the Sonnet 3D field solver, but I have seen no white papers or data verification. And therefore, I say take the Saturn PCB with a grain of salt, use it, but definitely verify it with your fabricators. Okay. Current flow. As current or EM energy flows in a trace, heat is generated due to the power dissipated from voltage on the trace. This goes back to Watt's law that we should have all learned in fundamentals of electrical engineering or engineering technology. Power is voltage times current. The trace width for power is going to be determined by the cross-sectional area. As we saw previously, the thickness of copper is measured in ounces per square foot. With legacy values, we're updated to use metric. These are the legacy values right here for ½ ounce, 1 ounce, 2 ounce, and 3 ounce. The ones we saw in the chart earlier are the updated ones, which now standardized on metric. The legacy ones standardized on imperial or English, and metric was the secondary. IPC is standardized on metric with English as the secondary, and so on. Right here. And the thicker the copper is, the narrower the trace can be to carry the same amount of current. However, thin, wide traces tend to dissipate heat to the surrounding environment more efficiently than thick, tall traces. You would think that the tall, thick traces act like heat sink fins, but it turns out because of the solder mask coating and so on, that the wide, flat traces, we get the benefits of the convective cooling, right? Where heat, the heat from the trace heats the air, you get the convective air currents and so on. So you get the convective cooling as well as the conductive cooling effects. Now, how do we size our traces right here? So in the Legacy 2221A, we had these 3 charts here. We have sense, and what we have for you now in the course is 2152 or IPC 2152 right here, which is a updated and expanded set of charts to include both imperial as well as metric, as well as air and vacuum environments, as well as a broader range of both lower temperature rises and higher temperature rises and so on. But effectively what you have right here is you have external and internal traces right here. So you have current that you need to carry here, and temperature rise above ambient here with a cross-sectional area. Whether internal or external here, you will then take that cross-sectional area, come down to the middle chart right here, find your cross-sectional area, come up to intersect with the line that represents the copper weight you wish to use, and that will come over here and tell you how wide the trace needs to be in that thickness to get that cross-sectional area. So we'll do a quick walkthrough of how that would work here. So looking at, this is the one for the external, the internal one, the legacy chart that's no longer around that was in the 2221A. The legacy chart was simply a 50% derated values of what was in the external chart. Again, IPC has since gone and done, commissioned a research where a number of folks went in and did the research and actually got newer, better empirical data based off of the structures and so on. And so we go over here, and what we see are temperature rise, and this is temperature rise above ambient. This does not mean the absolute temperature you're going to measure on the trace. So for example, if you're operating, and I'm just going to use my area where I'm at right now, the Sacramento, California area, in the summer, it easily gets to 110 degrees, outside air temperature. And if you're in a machine room for an elevator that's on the roof of the high-rise building in downtown, it's easily 130, 140 degrees Fahrenheit inside that building, right? So if we say right here, and we'll just do a little math right here, units, temperature, if I'm at 140 degrees F, that's 60 degrees C, right? So if I'm already at 60 degrees C and I've designed my trace for 10 degrees C rise, that means I will measure an absolute temperature of 70 degrees C, right? I'm not just going to measure exactly 10 degrees C. I'm going to measure 10 degrees hotter than ambient, right? And so that's what we're really talking about here. This is rise above ambient that you are willing to tolerate, okay? So once I've determined that, I would then come down here, and again, I would do the copper weight to cross section right here, and looking at how that would work right here. So if I were to take this as an example, I have 10 amps of current, I want 10 degrees C rise, I want 1 ounce copper, and I want it to be external copper. So I would come to my external copper chart right here, I'd find my 10 amp line right here, I would bring that over to 10 degrees C, I would come down here to my cross-sectional area, I take the same cross-sectional area, rise it up here, and bring it back over here, and see that I'm at about 300 mils for my cross-sectional, for the width in 1 ounce copper to get the 400 mils of cross-sectional area. All right. Cool. Any question on the basic material we covered today? Yes, no? All right. Well, if there are no questions, I will give everybody, what do we have, like 6 minutes back, 7 minutes back, something like that. We'll call it an early day here. We will meet again Wednesday morning. I will introduce the Altium tool. I will introduce the project start point where we were at, and so on and so forth, and go from there. All right. Any other questions on any of the stuff that we have today? Right. If there are no questions, I will say welcome everyone. I look forward to having a fun and exciting course with you all this time around, and I will see everybody on Wednesday, and have a good day.
Thank you. See you soon.
Thanks, Chris.
Yep.
Cheers, Chris.
Cheers.
Chris, if you want to stop the recording, we can just hang on.
Yep, we can do that. I will stop the recording.
Thank you, Chris.